Hello everyone, I am Dr. Geetha, Head and Associate Professor, PG and Research Department of Chemistry, Sri Sharada College for Women, Salem 60. In this video, we are going to learn about Lindemann Theory of unimolecular reactions. Theories of reaction rates of unimolecular reactions, we have collision theory of bimolecular reactions as the foremost one. In that theory, it tells about the collisions that occur between two reactant molecules. But in the case of unimolecular reactions, the concept is different. How it is different from how it is different from unimolecular reactions. To know these ideas, we have to learn about what are unimolecular reactions. Here, some of the unimolecular reactions are given as examples. The first one is thermal decomposition of azomethane gas at high pressure. Next, we have the decomposition of ethyl iodide and isomerization reactions are given as examples for unimolecular reactions as third and fourth one. In all these cases, we come across a single step product formation. These are examples of unimolecular reactions. Which reactions are unimolecular reactions? It is based on the idea of the number of molecules that take part in a single step. When you have one molecule taking part in a single step elementary reaction, it is called unimolecular. And if you have two molecules involved in an elementary step reaction, it is called as a bimolecular reaction. And if you have three molecules taking part in a single step occurring elementary reaction, it is called as a trimolecular reaction. So the molecularity term is applicable only to elementary reactions. And what are these elementary reactions? Reactions that involve chemical species of only one type in a reaction to give the product, they are called as elementary reactions. These reactions do not involve any chemical species as intermediate and directly they will produce the product. So such reactions are called as elementary reactions, and molecularity term is applicable only to those reactions which are having only single step representation. They are different from complex reactions where you have so many reactions occurring as single step to give the final product in a complete reaction. Before we go in detail about Lindemann theory of unimolecular reactions mechanism, let us see about pre-equilibrium approximation. The pre-equilibrium approximation is a general concept what is employed in the evaluation of reaction mechanisms. It helps us to understand the kinetics of various unimolecular reactions and other reactions which are having a pre-equilibrium formed between the reactants and the intermediate named as I. Here I have given the example of a reaction where you have two reactants A and B react to give the intermediate I, and that intermediate formed may react back to give the reactants A and B by a second decomposition step represented with the rate constant K inverse, and either it may give the reactant back or it may decompose to give the product. So such an example is the pre-equilibrium approximation concept. Here you see an intermediate which is established before product formation occurs. Here the forward reaction is represented with the rate constant Kf, and the backward reaction for the intermediate formation is represented as Kr. If the forward and backward reactions involving the reactants and intermediate are more rapid than the decay of the intermediate to form products, which is the final step, then the reaction of equation 1 can be imagined to occur in two distinct states. In the first step, equilibrium between the reactants and the intermediates is maintained during the course of the reaction. That means A and B react to give the intermediate, and that establishes a reaction with an equilibrium mechanism. The second step, the intermediate undergoes decay to form product. That is, after the equilibrium existence, there exists a time lag, and during which the first step may give the intermediate, and that intermediate may decompose to give the reactants again back. Whereas the second step, the intermediate undergoes decay to form product. This description of events is referred to as the pre-equilibrium approximation. That means you have a product formation, and before which you have an existence of an intermediate formation, and that intermediate may create a equilibrium between the reactants and the intermediate. Such an idea is called as pre-equilibrium approximation. The differential rate expression for the product formation Kp is given as dP by dt is equal to Kp into I. Here Kp is the rate constant for the product formation step, and I is given in square brackets representing the concentration of the intermediate, for which we are going to apply the equilibrium constant equation. What is Kc? Kc is given as rate of forward reaction divided by rate of backward reaction. When we apply that here, we will find out what is the concentration of I, that is given as I is equal to Kc into A into B concentration terms. This concept we are going to apply in the net reaction rate, where dP by dt is given in terms of concentration of I, the reactive intermediate formed during the course of the reaction. When we substitute the I value here, we will arrive at the equation Kp is into Kc into concentration of A into concentration of B, which is equal to K effective rate constant. The two rate constants Kp and Kc are replaced by a new rate constant K effective into concentration of A into concentration of B. With the idea of pre-equilibrium approximation, let us enter into Lindemann mechanism for unimolecular reactions, which provides an elegant example of the relationship between kinetics and reaction mechanisms that are applicable to unimolecular reactions. The mechanism was developed to describe the observed concentration dependence in unimolecular dissociation reactions of the form A giving fragments. The question here is, how does the reactant molecule require sufficient energy to undergo decomposition to give the product? It is a single molecule, and how that energy will be possessed by the molecule to go for bond breaking, which will result in the product formation. One possibility is that the reactant acquires sufficient energy to react through bimolecular collision. If it is the bimolecular collision, means how it will occur in the case of a unimolecular reactions. Here, the reactant molecule reacts with another reactant molecule of the similar type A, reacting with A to give the product formation, and that will happen through the intermediate, which is now the energy rich active intermediate. The Lindemann mechanism is supposed to occur via two steps. The first step, the reactants acquire sufficient energy to undergo reaction through a bimolecular collision given by equation 2. Here, the reactant A reacts with another reactant of similar type A, undergoing a collision to give A star, which is represented a molecule with excess energy, and another reactant going out as simple A with lesser energy. In this energy reaction, A is the activated reactant by through bimolecular collision that has received sufficient energy to undergo decomposition to give the product, whereas the collisional pattern of the activated reactant molecule leaves collision with insufficient energy to decompose. So that is how the first step occurs. Once the activated intermediate A star has been formed, means, according to Lindemann, the second step will occur after a time lag, during which the A star is having options to form the product via decomposition of product step represented by the second equation with the rate constant K2, or it may undergo deactivation, which is given as A star plus A giving A and A. Here the reactive intermediate A star is having some time to choose between the deactivation step or the decomposition step. Deactivation means it will lose its energy by collision with another simple reactant A of similar type, whereby both the molecules will undergo collision and the energy has been replaced from the active intermediate which it has acquired by bimolecular collision in the first step. So the second option is here it is going deactivation. And another third step is the original product formation step where the active intermediate without any further collision A star, it is going to give the product represented by the equation A star giving product, and the rate constant here is represented as K2. So we have three rate constants representing the three steps as proposed by Lindemann, where A reacting with A to give A star and A the first step, and the second step involving A star and A going to give the original reactants with equal energy A and A, and the third step A star giving product, which is the final product formation step. Thus, the Lindemann mechanism implies that a separation in time scale exists between activation and deactivation product formation steps. Out of these three steps, where we have the product formation. So, when we inspect the mechanism described by equations 2 and 3, they demonstrate that the only process resulting in product formation is the final decomposition step, which is given by the equation 4. Therefore, the rate of product formation is written as equation 5, where dP by dt is equal to K2 into A star, which is our active intermediate that has been formed during the course of the reaction, from which we have to identify the rate of formation step and the rate of decomposition step, so that we can substitute the concentration of A star by making use of steady state approximation. So to arrive at the concentration of A star, which is the active intermediate formed during the course of the reaction, we are in need of rate of formation of A star and rate of decomposition of A star, so that we can substitute that in equation 5. So if you want to do the evaluation of equation 5, we are going to write the rate of formation of A star in and its rate of decomposition, which are shown in this equation. dA star by dt is equal to K1 rate constant of the forward reaction, that is the first step for the equilibrium existence, into concentration of A square minus rate of the backward reaction, which is represented as K inverse into A into A star, minus the rate of decomposition of A star, which can occur by the third step also, what is known as decomposition step, K2 into concentration of A star, which is equal to 0. This is known as steady state approximation concept, by means of which we are able to arrive at the concentration of A star. So when we bring the like terms on the same side, and if we have A star alone on one side, we'll have K1 into A concentration square divided by K inverse into concentration of A plus K2, which will help us to substitute A star concentration in equation 5. The net reaction rate is given by equation 8, which shows that dP by dt is equal to K1 into K2 into A power 2 divided by K inverse 1 into concentration of A plus K2. In this equation, the first order dependence or second order dependence of any reaction is determined by making use of the relative concentrations of the two terms involved in the denominator here in equation 8. The equation is the central result of the Lindemann mechanism. It states that the observed order dependence on A depends on the relative magnitude of K inverse 1 versus K2. At high concentrations, if we have K inverse 1 greater than K2, and equation 8 in that case reduces to equation 9 as shown below. So equation 9 demonstrates that at high substrate concentrations or at high gas pressures, it is the product formation to follow first order in A consistent with the experimental result. Mechanistically, at high pressures, activated molecules will be produced faster than decomposition occurs, such that the rate of decomposition is the rate determining step in the product formation. Whereas what happens at low concentrations is the rate constant K2 will be greater than K inverse into A, and equation 8 will change into equation 10 that has been shown in the next slide. The net reaction rate given as dP by dt will be equal to K1 into concentration of A squared. The equation 10 demonstrates that at low pressures and at low concentrations of the substrate, the formation of activated complex becomes the rate determining step due to the availability of the reactive intermediate to form the product, and it is the product formation step which shows that the rate is second order with respect to the proposed mechanism. The Lindemann mechanism is thus generalized to describe a variety of unimolecular reactions through the following scheme, which is generalized as the reactant A reacts with another reactant of similar type M, or it may be M may be a collisional partner, which is a non non-reactive buffer gas which is added to the reaction, and these two reactants react to give the energy rich active intermediate which is known as energized species of reactant A, represented as A star, plus another less energy having reactant M. This first step is called the forward reaction, whose rate constant is given as K1. During which you are having a time lag after the forward reaction, and during that time lag it may undergo two types of reactions. Either it may get deactivated or de-energized, whereby the A star having extra energy will be losing its energy by another collision with the reactant M having less energy, or it may get decomposed to give the product. So we are having two chances: either the A star get deactivated to become the original less energy A by sharing its energy to the reactant M, or it may give the product by decomposition with the rate constant K2 representing the rate determining step in which you have the product formation. Thus, in this mechanism, M in the equation represents a collisional partner that can be the reactant itself, which is A of similar type, or some other species such as a non-reactive buffer gas added to the reaction. Thus, the generalized scheme for the Lindemann equation to give the product formation can be written as dP by dt equal to K1 K2 concentration of A into concentration of M divided by K minus 1 into concentration of M plus K2. We are having three rate constants in this final rate equation: K1, K2, K minus 1, all representing the rate of formation of A star, rate of decomposition of A star by deactivation and decomposition steps, and we are going to replace these three constants by a single constant represented as K uni, which is representing the rate constant for any unimolecular reaction, and that is given here as K uni into concentration of A. So that equation 11 is the general final representation for any unimolecular reaction which follows Lindemann's unimolecular reaction mechanism. K uni is the apparent rate constant for the reaction defined as K uni equal to K1 K2 into concentration of M divided by K minus 1 into concentration of M plus K2. Okay students, so far you have learned how Lindemann unimolecular reaction mechanism can be studied with the idea of pre-equilibrium approximation and steady state approximation, and how it changes into two different equations at low pressure and high pressure concentrations of the substrate molecules. And hope you had a good learning session. Thank you all.